Hello, everybody. Welcome to Unit 1, Lesson 19 on evidence, angles, and proof. Some of the important things we're going to do in here, we're going to prove that vertical angles are congruent. We're also going to identify some other kinds of important angles, such as adjacent angles, linear pairs, complementary and supplementary angles. I would make sure that you open up the activity and try and follow along as I'm going through the video. It's a cool thing to do. First and foremost, though, this diagram on the left here, it has three numbered angles, angle 1, angle 2, and angle 3. They could be given other names, though, naming them using three-letter combinations. I'm sure your teachers have talked about that a little bit. I want you to pause now and try and give the angles as many good names as you can come up with. Okay, hopefully you paused there and tried some stuff out. Here's all the ones that I have. Boosh. Whoa, there's so many. Highlights here. Remember that for any angle, if you're naming it with three letters, the middle letter needs to be the vertex. Like angle 1 could be called XZY or YZX, and those would be just as good. I would also say it's the only angle in this picture that can be called just angle Z, only one letter, because there's no other angles that have a vertex at Z. Now, I wouldn't call these angles, angle Y or angle X, because technically there's four angles that have a vertex at X, and so it wouldn't be very clear about which one you were talking about. But yeah, all of those other names are good. On this page, adjacent angles, the first of our terms. Adjacent angles are two angles that share a common side and vertex, okay? So DCE and BCE are adjacent angles because they share a vertex at point C and they have this middle side together, CE, that they both have. Now, if I know that DCB, the big angle, is 50 degrees, then what would you guess is true about the other two angles? Make a conjecture. That's a fancy word for guess, or this is something I think might be true. If I go ahead and measure those angles to find out if we're right, if you said that those two angles should add up to 50, you would be correct. You would be for sure correct. And that's true even if I move point E around. And I hope that makes sense conceptually, like the two angles, they fit completely inside of the big angle. They should add up to 50, right? All right, enough said there. Linear pair is the second most important term in this presentation. A linear pair are two adjacent angles that form a line together, like DAB and CAD. Okay? Together, they form this line CB. And every time you see this happens, those angles must add up to 180 degrees. So if, oh no, I already have the answer right here. Whatever. DAB has a measure of 70 degrees, then I know that CAD must have a measure of 110 degrees. And even if I move those points around a little bit, you will see that no matter what, those two angles together will add up to 180 degrees, which is a cool thing to do. Okay, so be on the lookout for linear pairs. They're important. And that's what you're going to need to use on this page in order to fill in the other missing angle measures. However, there's the most important term, I would say, on this page. Vertical angles are a pair of opposite angles at the intersection of two lines. So angles FEG and IEH. I answered this one right here, FEG and IEH. Okay, those ones across from each other. Those are vertical angles. So in theory, you should be able to hopefully name the other pair of vertical angles in this figure and find the missing angle measures and type that in the box down below. If you've taken time to do that, I hope you came up with something that looks a little bit like this. Okay, hopefully you came up with something along these lines. The obtuse angles here both have to be 150 degrees because FEG is a linear pair with IEF, and therefore 30 plus 150 makes 180 for the straight line. You can make the same argument for FEG with HEG, that they would have to be a linear pair and therefore make 180 degrees. Interesting fact, the other vertical angles, IEF and HEG, do you notice what happened here? They're the same. And the same thing could be said for the other two vertical angles, FEG and IEH. They're also the same measurement. They're congruent. I wonder if that always happens. Yes, that always happens. Vertical angles are always the same measure, just like linear pairs always add up to 180. Well, why is that true? Because Mr. Martin said so? That doesn't seem like a very good argument. Could we prove it? Could we have sufficient evidence to say that this is true every single time? Let's think about why that might be true for a second here. Okay, my first argument goes something like this. You'll notice that I added some labels to these points and some measures to these angles. So I don't know what specific numbers these are, but I'll say that the measure of angle LKJ is A, and so on. Here's how my argument goes. I am sure that these two angles with measures A and B would add up to 180 because those two angles are a linear pair. Likewise, the two angles with measures B and C would add up to 180 because they are also a linear pair. So if A plus B equals 180 and C plus B equals 180, it seems reasonable to say that A equals C, right? That's one possible argument for it. I'm going to show you a different one, though. 1 second. The other argument goes a little something like this. We talked about rigid transformations in our last couple of weeks, and we know that rigid transformations can produce congruent figures, right? So if I rotate this entire figure around the point K, let's try something like this, okay? So I'm going to do a rotation of the entire figure around point K. So first, I'm applying to this entire figure a rotation by 90 degrees. That's not going to look right. I'm going to do a rotation of the entire figure by 180 degrees. What does that do to it? Oh, well, it lands right on top of itself. So the original angle LKM, when rotated by 180 degrees, basically lands in the same place as the angle JKN did. So because those two shapes landed right on top of each other, I'm going to conclude that those angles must be congruent because rotations should create congruent figures, okay? And they completely coincide with each other. I don't know. That's the argument for now. To be honest, the other argument makes more sense to me. But, you know, both of them are valid in one way or another. At the end of the day, I need you to know that vertical angles are congruent, and it's a big deal, and it's going to keep coming out throughout the year. So be on the lookout for this image. Vertical angles, they are congruent. What else do I want to say before we get out of here? I think that there are a couple of other terms that we would like to define. So I'm going to go to this next page here. If you want to answer the question in here, that's fine. But the other thing that we want to talk about is supplementary angles, which are angles that add up to 180 degrees, and complementary angles, which add up to 90 degrees, okay? So based on those definitions, I want you to take a moment and answer the questions on these 2 pages about supplementary and complementary. Okay, here's some stuff I came up with. Notice that the first 2 I listed are just linear pairs, and even without measuring, I know that those have to add up to 180, although if you wanted to double check your work, I guess you could use the angle measuring tool in these examples. The other thing that would be supplementary is this triplet, these 3 angles. And I know that they would add up to 180 because those are the 3 angles inside of this triangle. And triangles always make 180 degrees. As far as things that add up to 90 that are complementary, here's a couple of pairs that I came up with, and I measured them on here just to give you some better ideas about how I'm making those decisions. Anyway, last bit for now. I want you to make a notice and wonder statement here. What do you notice and what do you wonder about this? Okay, well, whatever you said. On the next page, here's what Diego thinks. Here's something that Diego noticed about this. He noticed that all of those dashed lines tended to make right angles. That's interesting. And also, each of these appears to be a bisector of the angle. And on this page, I've actually built that particular construction. So these red lines are definitely angle bisectors. I've built it that way. So I want you to try and look at Diego's conjecture and see what you think about it and see if you can prove it. See if you have any reasoning to back that up. But at any rate, I'm going to say at the end of the day, I want you to know going forward that being able to prove things is pretty important in geometry. Being able to explain our reasoning. We've had, a fair amount of practice with that before, but going forward, even more so. If you want to be able to say something is true all the time, you better be able to back it up. So consider these things, and if you have any questions, type them in at the end of the video. Thanks, everybody.